Hello everyone, welcome to my channel, the Civil Channel 25. In this video, I am going to explain about the strength of materials, the Unit 1, simple stresses and strains. So what is strength of materials? Mechanics is science which deals with the study of forces and their effects on members, structures and fluids. See, here how much is the material strength and what are the forces involved in this, and when member is subjected to the external force, the member is getting deformed or displaced. So see, for example, this is one block. See, we are applying one force. Here this block will be either displaced or deformed. If this is deformed, it is called as static equilibrium. See, this is one block. See, this one is the block, actual original block. From this side, from left side, we are applying the force. See, we are applying the force. This is displacing. Displacing means from this position to this position it is changing, but no change of the shape. See, this is known as the displacement condition. X dash, X dash. And see, when on one body, if load is applying from left side or else right side, see, at this point it will be constant and this will be deformed. Deformed means it will be moving like this. So this is known as the deformed condition. In deformed condition, the change in the shape or dimension happens. And this mechanics is of three types: engineering mechanics, mechanics of solids, or strength of materials, or fluid mechanics. See, what is engineering mechanics? Engineering mechanics means mechanics of the rigid bodies. Rigid bodies is known as engineering mechanics. And this study will affect the external forces on the rigid body. External forces, when we are only applying the force from left side or right side. So this will be in engineering mechanics. In engineering mechanics, no change in relative position of particles, even in the presence of the external forces also. So deformation is internal resisting force will be 0. And coming to the mechanics of the solids. See here, mechanics of deformable bodies. See here, the body is deformed. This will be coming under the mechanics of the solids. And the study of the internal resisting forces, change in dimension or change in the shapes. Coming to the fluid mechanics. The mechanics of compressible fluids or incompressible. The basic objective of the strength of materials is to derive the expressions for deformations, stresses, strains caused due to the external loads. And also these expressions are used to designing of the structures also. See, first of all, we have to know what is the strength. What is the strength? Strength is the ability of the material to resist the failure. The ability of the material to resist the failure under the external loads. When we are applying the load, the material should be resist the failure against the external load, or maximum value or limiting value of the stress that can withstand without failure. That is known as the strength, and it is the property of the material and is constant for the given material. Strength is the primary design parameter also. And next we have to know what is the stiffness also. So here the stiffness is defined as the ability of the material to resist deformation. Stiffness means the ability of the material to resist the deformation. Stiffness is also a material property. It is the secondary design parameter. And here see, when the deflection increases, stiffness decreases. See, when the deflection increases, the stiffness will be decreasing. And when the deflection is increasing, the flexibility will be increasing. It will be, both are reciprocal with each other. When the deflection is increasing, stiffness will decrease. When the deflection is increasing, flexibility will increase. These both will be reciprocal to each other. Coming to the assumptions made in the strength of material equations. First one, material is assumed to be solid and continuous, and no cracks and no voids in the material. And next one is homogeneous. In homogeneous means in a given direction at every point the material exhibits same elastic properties. That is, elastic properties are independent of point and it depends on the direction. Elastic properties are independent of the point and it depends on the direction. All base materials without any mixture like wood, iron, gold are example for the homogeneous. Wood, iron, gold are example for the homogeneous material. Here the material is assumed to be homogeneous in one direction and also isotropic. See here, this one is the homogeneous, same direction, one direction, and for EX also, same as it is. And next one, coming to the isotropic. Isotropic means it is the material exhibit at one point in all directions, one point in all the directions. Then the material is said to be the isotropic. See here, the example for the isotropic is iron, brass, silver, etc. And next one, all fine grained materials also will be under the isotropic, examples of the isotropic. Next assumption is homogeneous and isotropic. A material should have same composition and same elastic properties in the all directions. Example, iron, silver, gold, etc. And next one, the material orthotropic. Orthotropic means it will be having 9 elastic constants. Orthotropic means at one point a material exhibits different elastic properties. Material exhibit different elastic properties and these three will be mutually perpendicular direction. These three are mutually perpendicular directions. Here Ex is not equals to Ey is not equals to Ez, and all orthotropic materials can be isotropic, but all anisotropic materials cannot be orthotropic. All orthotropic materials can be isotropic, but all anisotropic materials cannot be orthotropic. So, note 2. Here the materials will be of three types. There are anisotropic, allotropic and non-isotropic. See here, anisotropic or allotropic or non-isotropic. These three names are same. This defines at given point in different directions different elastic properties. See, this one is the point and different directions E1, E2, E3, E4, E5, and the directions are different and elastic properties also different. So here this one will not be equal to this one. This one also will not be equal to this one. E3 will not be equal to E4 and E4 will not be equal to E5. So therefore E1 is not equal to E2 is not equals to E3 is not equals to E4 is not equals to E5. Examples are sand, glass with crack. And next one is self weight of the member is also ignored. See, this one is the deformation. This one is the P, change in length, and P. Here self weight is equals to 0. Here self weight is not equals to 0. And superposition principle is valid. Superposition principle means the effect of the various parameter is algebraic summation of the individuals. See here, this is the various parameter. This one, this is the twisting moment, and here this tends to, this load is acting downwards, so from this side it is acting upwards and upwards. See, if we take this into individual, it will be like this. This is known as a superposition principle, and combined effect of the system on rigid body is the sum of the effect of the each individuals. Next assumption is member is assumed under the static equilibrium condition, and Saint-Venant's principle is valid. Saint-Venant's principle means sudden change in any parameter causes stress concentration and leads failure of the member. See, According to the Saint-Venant's principle, if cross section is far away from the load, then stress distribution on the cross section is independent. If nearer, then stress distribution is dependent. See, this one is stress concentration region. See, here if cross section is far away from the load, then stress distribution of the cross section is independent, and if nearer, then the stress distribution is dependent. This one is wrong and this one is right. See, and coming to the limitations, the member must be linear elastic, that is loads acting on the member must be in the proportional limit, that is Hooke's law is valid. Within the proportionality limit, stress is proportional to the strain. This is known as the Hooke's law. And see, here this is the proportionality limit and this is the stress and this is the strain. This is next one, the slopes and deflections due to the loading is small as possible, and the superposition principle is not valid in the case of impact loads, strain energy, deep beams, long columns, sinking of supports, non-circular shafts subject to the torsion. Example, strain energy concept. See, here the load is, the force is applying like this. See. And coming to the load, an external force or couple to which a component is subjected during its functionality. Classification. Loads are classified under with respect to time, with respect to direction and with respect to the area. First, with respect to time, there are two types of load, static load and dynamic load. Static means magnitude and direction remains constant with respect to time, and dynamic means magnitude and direction both changes with respect to time. In these static loads, there are two types, dead loads and gradually applied loads. Dead load means weight of non-living components are called dead loads. Example, weight of the shaft beam column. Gradually applied load means variation in magnitude but direction is constant here. The variation in magnitude is negligible with respect to time. Coming to the dynamic loads, there are also two types, impact or shock or suddenly applied loads, or fatigue or cycle variable loads. Here see, fatigue loads means it will be repeating, the cycles will be repeating. This will be under the dynamic load. This is the gradually applied load. Time required to reach the maximum value is more. Here the graph is taken as load and time, and here the load is constant, that is Pmax. This is the gradually applied load. All gradually applied loads are represented by their maximum value or amplitude. Next, impact or shock loads. Impact or shock loads means acting over a short interval of time period. Example, punching machine, punching operations, forcing operations. Next one, fatigue or cyclic or variable loads. These loads are applied repeatedly with respect to time. Example is automobile transmission shaft. These all are before one, all the loads with respect to the time. Now load with respect to the direction. There are two types, normal loads and tangential or shear loads. Normal loads means this will be acting perpendicular to the cross-sectional area, concerned or parallel to the longitudinal axis. And tangential shear force means acting parallel to the cross-section or area concerned to the perpendicular to the longitudinal axis. These normal loads also, these are of two types again, axial load and eccentric axial load. These tangential shear loads also two types, transverse shear load and eccentric transverse shear load. And next one, the loads with respect to area. With respect to area are concentrated loads and distributed loads. Concentrated loads are concentrated point load, concentrated moments. And distributed loads means uniformly distributed load, uniformly varying load, uniformly distributed moment, uniformly varying moment. Uniformly distributed load means, see, the load is distributed like this, see. And uniformly varying load means the load is varying, this one, this, like this, it is varying. Uniformly distributed moment means equally it is distributing the moment. And uniformly varying moment means, see, it is varying. Understand? And next one, concentrated point load. This one is the concentrated point load and this one is the concentrated moment, that is couple. Coming to the stress. Stress is the magnitude of the internal resisting force at point against the deformations caused due to the external loads. Stress is denoted by the sigma, internal resistance force by cross-section area. At equilibrium, internal resistance force is equals to external applied force, as we told before. So sigma is equals to P by A. When the body is to one body, if force is applying like this, to one body force is applying like this from this side, the body will be trying to resist. So this one is known as FR, sigma FR. So this one is at equilibrium, internal resistance force is equals to external applied force. So P is equals to sigma FR also. And example C, as it is resisting. Understand? Units of this stress are Newton per meter square, and dimensions of this stress are, see, dimensional formula is m L power minus 1 and T power minus 2, and units of this stress are Newton per meter square or Pascal. 1 Pascal is equals to 1 Newton per meter square, kilopascal, megapascal and gigapascal. 1 kilopascal is equal to 10 cube, 1 megapascal is equals to 10 power 6, 1 gigapascal is equals to 10 power 9. Coming to the conclusions, when next, comparison between stress and pressure. See, stress is internal phenomena but pressure is the external phenomena. The magnitude of stress is equal in normal direction and tangential direction, but magnitude of pressure remains same in the all directions, and stress will be acting parallel to the surface or normal to the surface, but pressure always acting normal to the surface. Stress is a tensor quantity but pressure is a scalar quantity. Due to the stress, pressure will not be developed, but due to the pressure, stress will be developed. Pressure can be measured by pressure gauges, but stress cannot be measured directly. And coming to the classification of the stresses, according to the direction of the loading, stress is classified into two types: direct stress and indirect stress. Direct means are due to the direct loads. Again, this direct stress is of two types: normal stress and shear stress. Indirect stress due to the bending moment or torsion or twisting moment, normal stress and shear stress. Normal stress means it is under direct stress acting perpendicular to the area concerned, cross section. See here. Here the stress is acting. So sigma T is equals to P by A. Tension. See, it is acting like this. So this is tension now. If it is acting like this, then it is compression now. Tension means positive. See, sigma T is equals to positive P by A, tension. Sigma C, compression, is equals to minus P by A, compression. Understand? And see, stress also is acting on uniaxial state of stress, means only one direction it is acting, sigma x. If it is acting in two directions, sigma x, sigma y, then it is known as biaxial of state of stress. Then it is if it is acting in three directions, x, y, z, then it will be a triaxial state of stress. Coming to the shear stress. Shear stress means acting parallel to the cross section of the area. Shear stress is denoted by is equal to F by A. Normal stress under indirect stress. It is due to the bending moment. See, normal stress is equals to F is equals to M by Z. Shear stress due to the twisting or torsion moment.